In this video, we're going to look at the law of sines and the law of cosines again, but we'll focus on more real-world applications where these two laws are helpful in helping us solve problems. So we're going to take a look at a couple examples, and both of them actually talk about either a heading or a bearing. So we're going to just talk about those that idea real quick. So when we talk about either a heading or a bearing, we're referring to the direction that something's headed. So we're typically talking about like an airplane or a boat or something like that. So this notation here, when I say n 30 degrees E, what that means is that I am going 30 degrees east of due north. Okay, 30 degrees east of due north. So that literally means you start with this idea that I'm pointed due north, and then from that line you go 30 degrees. And then that's the direction that you're heading. So that's what we mean when we use this notation here. So in this example below, we'll use that notation as well. So it says a ship leaves port at 1 p.m. and travels 35 degrees east of due south at a rate of 24 miles per hour. Another ship leaves the same port at 1:30 p.m. and travels 20 degrees west of due south at 18 miles per hour. Approximately how far apart are the ships at 3 p.m.? All right, so let's start by just sketching a picture. So I'm going to start with a due south line here, because both of these are being measured from the due south line. So on the one hand, I'm going 35 degrees east of that. So just approximate that the best I can. So let's call that 35 degrees. Okay. And I'll go ahead and stop there for now. Put 35 degrees there. And then the other one is 20 degrees west of south. Okay, so I'm not going to make quite as much of an angle. And I'm going to purposefully leave this line quite a bit shorter than this line, because for one, the 35 degrees east of south ship left earlier and it's traveling faster. Okay, so I know that really this one should have covered way more distance. So here's 20 degrees from there to there. Okay, and so if I'm saying approximately how far apart are the ships at 3 p.m., we're saying, okay, at 3 p.m., what is this distance here? All right, so I really know this angle in here, okay, so using a different color, right? If we have 35 degrees here and 20 degrees here, I do know that overall, that whole thing has to be 55 degrees. Okay, so I know this angle. And they give me all this information about how fast they're going and also how long they've traveled, so that should be enough for me to be able to figure out the distances that each of them have traveled. Okay, so ship number 1, which is this one over here, traveled from 1 p.m. to 3 p.m. So it traveled for 2 hours at a rate of 24 miles per hour. So 24 miles per hour times 2 hours is going to give me 48 miles. This one, the ship number 2, only travels for an hour and a half, right? So this one I'm going to take its speed, which is 18 miles per hour, times 1.5 miles, hours, not miles, and then I of course get 24 miles. All right, so I know an angle, and then I know these two sides, right, that form the angle. And so if you remember all of our work with with triangles using the law of sines and the law of cosines. This one's a prime candidate for the law of cosines because I am interested in this value here, this distance, and I know the angle opposite of it, and I know these other two sides. So I know that d squared should equal 24 squared plus 48 squared minus 2 times 24 times 48 times the cosine of 55 degrees. But if that's what d squared should equal, then d should just equal the square root of all of that. So applying the law of cosines, I get that this distance is approximately 39.5 miles. So let's take a look at another example. We have two towers that are located 7 miles apart on a mountain ridge. And suppose that Tower A is directly north of Tower B, and a fire is spotted bearing 70 degrees east of south from Tower A and 85 degrees east of north from Tower B. How far is the fire from Tower B? All right. So here's Tower A up here, and it says that Tower A is directly north of Tower B, so we can put B right there. And so we'll just connect those up with a nice vertical line. Okay, so Tower A, right? Tower A spots the fire at a bearing of 70 degrees east of the due south line. Okay, so it helps to kind of recognize, okay, here is 90 degrees east of the south line. So 70 degrees, might be something like this. Okay. I'll do my best to draw a semi-straight line. It's kind of hard to do on this sketch pad I have. And then for B, it's 85 degrees east of the due north line. So that's very close to 90 degrees, right? So there's 90. So really just barely shallower than that. So you can see this fire should be pretty far away. And so I'm just going to extend both of these lines out until I get them to intersect with one another. And then of course you can see I'm going to form a triangle, which then I have the potential to be able to apply the law of sines and cosines to. All right, so forgive me for not making these perfectly straight, but I think you get the picture here. So apparently here is our fire, right? And red for fire. There we go. All right, so let's go ahead and make sure we label those angles that we just went at. This is 85 degrees. And this is supposed to be 70 degrees, okay? And what do we know? The distance between Tower A and Tower B is 7 miles, okay? Now, as I look at this, we're asked how far from the fire is Tower B? So this is what we're looking for here. This is our x, okay? Now, we know that the law of sines allows us to take the sine of 70 degrees divided by x should be the same as the sine of another angle divided by its opposite side. Well, what we know is this opposite side of this angle, but they didn't give us this angle. But of course, if they give us the other two, we can always figure it out easily, right? Because all the angles in a triangle have to add up to 180 degrees. So we do that little bit of subtraction and we get 25 degrees. So we can pencil that in right there. And so now this is all set up where I can use the law of sines. Notice that I definitely don't want to use the law of cosines here because in the law of cosines you need to know two of your sides. So that's why law of cosines is out from the beginning. So we get in a position where we can use the law of sines. So now I can say that the sine of 25 degrees divided by 7 is going to equal the sine of 70 degrees divided by x. And, we can do our little cross multiplication there. The sine of 25 degrees is equal to 7 times the sine of 70 degrees. And then dividing both sides by the sine of 25 degrees will do the trick for me. So x is equal to this. But of course, we're interested in an approximation, so we can get a nice practical answer for how far this fire is away. And so when we do that computation, we should get about 15.6 miles. Okay, and although my picture was poor in the sense that my lines weren't exactly straight, I did a pretty decent job of making an accurate picture. Not perfect, but I suppose maybe this X should look a little longer. But if this is 7 miles, this should be a little over double that distance. So we know we would tell our fire crews 15.6 miles with this heading from Tower B is going to get to that fire.